Running Arch Linux and Omarchy on macOS historically required complex virtual machine configurations, manual display scaling tweaks, and fragile audio routing. Try Omarchy solves this by bundling a preconfigured ARM64 Arch Linux guest image, a custom-built QEMU runtime leveraging the Apple Hypervisor framework, and a native Swift launcher. This architecture delivers hardware-accelerated Linux desktop execution on Apple Silicon.
The repository brings the upstream Omarchy desktop experience directly to macOS without complex manual provisioning. Key capabilities include virgl graphics acceleration, native window resizing with dynamic resolution synchronization, bidirectional text and image clipboard integration via Virtio serial, host guest folder sharing using Virtio 9p, and strict lookback-only TCP and UDP port forwarding. Building Try Omarchy starts with an environment check using make.doctor. This verifies macOS 15, Apple Silicon hardware, Python 3, Swift 6, package config, and a running Docker engine. Executing make build run initiates a cached build system. It compiles the QEMU GPU runtime, builds the ARM64 guest image inside Docker, and packages the standalone macOS application bundle. The architecture splits into three distinct layers. At the top level, a lightweight Swift and AppKit launcher manages window state, host permissions, and bridge processes. Below it, QEMU interfaces directly with macOS Hypervisor framework to execute ARM64 CPU instructions natively on Apple Silicon. Inside the VM, Arch Linux boots from a verified factory image, displaying via Virtio GPU and virgl directly into a Cocoa window.
Host integration relies on specialized virtualization channels rather than generic network sockets. Clipboard sharing uses a dedicated Virtio serial port carrying new line-delimited JSON between Swift pasteboard monitors and Linux WL clipboard agents. Shared folders utilize QEMU Virtio 9p with custom patches that map the guest UID and GID to user 1000, preserving host file permissions while making folder access seamless inside Linux.
To maintain complete build determinism, guest scripts like apply-omarchy-backports.py enforce strict cryptographic verification before applying patches to upstream Omarchy source code. The script validates SHA-256 digests of the target files both before and after applying git patches. If any file hash mismatches expected pre-image or post-image digests, execution immediately terminates, preventing dirty state propagation. On the host side, main.swift routes CLI arguments and manages background process lifecycles. It initializes dedicated bridge processes for native audio, clipboard serialization, and accessibility-based command key translation. Signal handlers catch SIGINT and SIGDERM through Grand Central Dispatch sources, ensuring clean QEMU process termination, socket cleanup, and persistent VM state preservation during app shutdown. Packaging the application is governed by build-app.sh. The script verifies staged QEMU runtime binaries, compiles the AppKit launcher, renders vector app icons, and bundles runtime dependencies into a self-contained macOS app structure. It enforces developer ID signing across all bundled dynamic libraries and QEMU executables, appending hypervisor entitlements required by Apple Silicon. Storage lifecycle management ensures isolation between factory artifacts and user data. The app stores persistent VM state at application support. Try Omarchy VM v1, keeping the original factory guest disk untouched in app resources. The Swift launcher detects guest image version updates, requesting explicit user confirmation before executing factory resets or migrating compatible storage structures. Upstream release updates are automated through make update Omarchy with a target release tag. The underlying Python script pulls the designated release archive, verifies file integrity, updates spec.json, and regenerates the pinned ARM64 Arch Linux package lock file. This workflow ensures local downstream builds stay aligned with upstream Omarchy commits while preserving reproducible build guarantees. The security model enforces strict network and host boundaries. Forwarded ports strictly bind to localhost IP address 127.0.0.1 on the host, preventing external network access to guest services. Shared folders require explicit menu selection and block sensitive host locations like the entire home root or library directory. Furthermore, code execution relies on pinned package digests and signed hypervisor entitlements. The underlying technology stack integrates Apple Silicon hardware primitives with Linux desktop virtualization tools. macOS Hypervisor framework handles CPU execution, QEMU, and virgl provide graphics acceleration, virtio 9p manages file system pass-through, and systemd units orchestrate Linux guest services. Swift 6 and AppKit bind these components into a unified macOS application interface.
Evaluating architectural trade-offs reveals clear operational boundaries. On the design side, native hypervisor acceleration delivers responsive Linux desktop performance with zero host configuration. However, video decoding remains CPU only, causing high-resolution video playback slowdowns. Additionally, disk updates across major versions lack automatic migration, requiring manual export and re-import of guest data. Try Omarchy demonstrates how combining native macOS hypervisor APIs, patched QEMU integration, and reproducible Arch Linux guest images can deliver a smooth Linux desktop environment on Apple Silicon. You can inspect the complete open-source codebase, test local builds using the Makefile workflow, or explore release DMGs directly on GitHub.